How does a phenomenon-based unit foster students' different understandings and uses of the practices in which they engage? And what role does the teacher play in this?
What questions does that make you ask?
What's happening to the bats?
What's happening to which bats?
The little brown bats. What's affecting them that isn't affecting the big brown bats?
Good, yeah, okay, so that's a good question.
That the big brown bats are going around and eating up all the food in the little brown bats.
So that could be a question. Does it have to do with there just isn't enough of the same food in the environment? Is that what you're asking? Okay, you can ask that, that's fine.
The students analyze and use data to define the problem of the little brown bat. My role was to support the students as they engaged in sense-making strategies about data representation. What are you observing?
That the one population is going down while the other one is going up.
Okay. What population is going down?
The little brown bass. And then the big brown bass is going up.
Okay, so what about that? What does that do to the total?
First, the total went down, and then it went back up a little bit, but generally it's just going down.
Okay. What about you guys? What questions that make you ask?
So it makes me ask, what is causing the decrease and increase in the two different species of bats? And is it the same thing? And if so, how is it affecting them differently?
A phenomenon-based science unit offers multiple avenues for sense-making. Students can approach the phenomenon from perspectives congruent with their own sense-making strategies, allowing groups of students to develop a multi-layered approach. So one of the great things about working in a group is that you can help students feel more secure. You can put them with people, or they can self-select into groups of people that really value what they know, that really value their addition to the group. And so the trick is to help these students understand that everybody's voice is important and that there are certain people who are a little more reluctant than others to verbalize what they're thinking. Sometimes those kids write down what they're thinking. Sometimes they feel better telling just one other person who verbalizes it to the whole group. So we've got some good observations. Let's think about now. Look at your chart. How are we going to represent that mathematically?
I think maybe a graph would be a good way to represent it mathematically.
What kind of graph?
I think a line graph.
Yeah, okay, line graph would be my first choice. Why is it yours?
Because it shows like the way that the two populations decrease over a certain amount of time.
Excellent, excellent. We'll be able to see maybe where they even intersect, which could be really cool. And once their thoughts are acknowledged as valuable, it gives them that little bit of an extra push to try it again next time. And we create scientists doing that. We are talking about the flexibility and thoughtful use of the science and engineering practices. That is, 1. Asking questions for science and defining problems for engineering. 2. Developing and using models. 3. Planning and carrying out investigations. 4. Analyzing and interpreting data. 5. Using mathematics and computational thinking. 6. Constructing explanations for science and designing solutions for engineering. 7. Engaging in argument from evidence. 8. Obtaining, evaluating, and communicating information. An example of flexible practices is students critically considering how they use the practice to connect the phenomenon to the world outside. If I said to you, could you count all of the growing things in here? You could. Why couldn't you?
Well, you could.
You could. Would you want to?
No.
Probably wouldn't want to. Why? It is not only important for students to know how to do the practice, but why this practice now, and why this way of performing the practice. And was the outcome the one we wanted? Was it a useful way to go about explaining the phenomenon? The idea on counting the different species within that meter was to think about what would be different where there was diversity in an environment, and was that important in what happened if you pulled one species out of the environment? Did it change what happened to the other species in the environment? So you got grass. What else is in there? Do you see anything besides?
Dead grass.
Okay, so you see dead grass, so I can write that. How would you count that? Students figured out how sampling works, which builds their skills in the fourth practice, analyzing and interpreting data.
And we could make a guess what it is, but I would just call it a purple stem.
You have to figure out how many different kinds of plants are in that square.
What other ones do you guys notice in here? Just plain old blades of grass?
When some students brought up a concern with the data they were getting, we supported their thinking.
There's like 3 in the whole thing, but we found 1 in our square. So if you multiply it by 100, which is what you have to do, then it says there's 100 of them. So what I feel like is we don't have a big enough test group, like, to really make it accurate for the whole square. And this is just 1 square, the entire playground. So I wouldn't think it was accurate if we're only measuring this small amount, because this doesn't have as much clover as over here.
So you're saying that it's actually a problem that you have a smaller section?
Yeah.
And there's also the plants that aren't in this, but they are in the rest of the field.
So what would your recommendation be? How would we solve this problem?
You have to count the big section.
Count the entire section to get a more accurate result?
Yeah.
Count a small section for things that are obviously a lot of, but then count the things with less.
So what were you saying about a focus group?
So like when you're doing an experiment and you don't have a very big focus group, your results aren't going to be accurate because there aren't enough people that have been tested that represent all the diversity among the entire group of people or whatever you're testing.
So maybe if you do a focus group with a small group of people, it actually skews the results because it's too small of a focus?
Yes.
What do you think scientists do to account for that and think about that?
If you only have a small enough group, you're not going to see all the diversity.
So what could you do with your class to kind of account for that?
So go in different places because we're just in this one area of the playground, but maybe there's something that grows up on that hill that doesn't grow over here.
Some people have interpreted the NGSS and the performance expectations for assessment as a drive for the development of a specific set of dimensions that students develop.
I said that for our reasoning, could we say that insects also carry diseases, so they could be dying from that?
So that would be a claim.
Right.
That would be a claim. It's true. If you want to say that and have evidence for that, that would be a claim.
The student's work, like that of a scientist, justifies the practice, weighing the utility of one practice over another, or modifying a practice to meet the context at hand. And this is flexible sense-making and figuring out. It is what makes phenomenon-based science in the NGSS such an engaging and inspiring endeavor.